All right, so what we're going to look at today is what's called the normal distribution. So I have just a picture here for you. We'll talk a little bit more about this. But just so that you notice, the normal distribution is perfectly symmetrical. And this might not be the best picture. This line should go down and down and get closer and closer and closer, but never really touch the ground like an asymptote. So technically it goes forever. Now what we see here, this little symbol right in the middle, is the mean. So when we talk about the normal distribution, because it is symmetric, the mean and the median are equal. So the middle is the mean, or the average. So next picture that we see, another normal distribution. X bar, just another way to symbolize that we're talking about the mean, goes in the middle. And you'll notice we're drawing up and down, going up +1 sigma, just to remind you. Sigma stands for standard deviation. So I'm going to talk about 1, 2, and 3 standard deviations going in the positive direction, and 1, 2, 3 going down. We have just a couple of rules. Rule number 1 says if I go down 1 standard deviation and up 1 standard deviation, this much in here is 68%. 68% of all the data will be between -1 and +1 standard deviations. Then we're going to see between -2 and +2. So all this gives us 95%. 95%, that's almost everything. Most of data is between -2 and +2 standard deviations. As a matter of fact, this is so common that anything outside of that is considered unusual. So here, this is pretty typical. Anything out here, unusual. Unusual. And anything out here, unusual or weird. But we do get one more rule. If we go out 3, -3 to +3, then all of this gives us 99.7%. Wow, okay, now we've got really almost the whole thing. So if you found a piece of data that was 4 standard deviations away, that would be totally bizarre, because 99.7% of data is between -3 and +3 standard deviations. Okay, kind of weird and abstract, so let's put some numbers and some actual data with it. All right, here's an example. IQ scores, this is what it means, approximately follow a normal distribution. And what we see here, N for normal distribution, we put the mean and the standard deviation with that. So for this particular example, the average or mean IQ score is 100 with a standard deviation of 16. So I'm going to go ahead and draw a picture of what that tells me. So here's my normal distribution. I'm going to put the mean right in the middle, 100. And then I'm going to include 3 standard deviations going up and 3 standard deviations going down. That should take me practically to the edge of my picture. Because remember, between -3 and +3 is 99.7%. So that should be almost the whole picture. All right, so if I'm here at 100 and I want to add 1 standard deviation, that means I'm going to add 16. So my next number is 116. If I want to add another standard deviation, that's a total of 2 from 100, well, I could just add 16 again. That takes me to 132. And I could keep going, add another 16. That takes me to 148. All right, and then I can do the same thing in the negative direction. So if I want to go 1 standard deviation down, that just means I'm subtracting a standard deviation. Or in this case, it's going to be 16. So if I subtract 16, that takes me to 84. Subtract 16 again, that's 68. Subtract 16 again, that's 52. That's my normal model. So what's it good for? Well, we know from the previous slide that 68% of data, since we're talking IQ scores, we could discuss people. 68% of people have IQ scores between, well, between -1 and +1 standard deviation, between 84 and 116. That also tells me that 95% of people have IQ scores between, well, -2, +2, between 68 and 132. That tells me that if I run across a person who has an IQ score lower than 68, that would be unusual. If I run into a person that has an IQ above 132, that is unusual. We also know that 99.7% of people have IQ scores between 52 and 148. So it just helps us understand what's normal, what's expected, and we'll do a little bit more with this shortly. All right, so I'm going to get you started on this one. The birth weights of babies follow a normal distribution. Maybe you've never thought about that before, but it kind of makes sense. We're going to have a lot of babies kind of in this middle range, a lot of birth weights that are close to that, and very few really small babies, and very few really big babies. So I'm going to go ahead and put the mean right in the middle, 7.6. And I'm going to include 3 standard deviations up and 3 standard deviations down. The second number, that's my standard deviation, tells me how far up and down to put in my picture. So I had to pull out my calculator here. I don't know that I know these ones. 8.9. If I add 1.3, 10.2, and 11.5. And I can do the same thing going down. Adding, or in this case, subtracting 1.3 to get my next standard deviation. All right, 3.7. So I mentioned that 95, this 2 standard deviations up and down, is usually considered when things are unusual. This makes a lot of sense to me, because when a baby is born that is less than 5 pounds, that's premature, that's kind of a little scary, probably going to be in the ICU. That's definitely unusual. And wow, I know very few people that can tell me they've ever had a baby above 10.2 pounds. So that would also be unusual. So I could write that. 95% of babies are born between 5 and 10.2 pounds. We could also talk about 68% and 99.7% and what that tells us about babies' birth weight. All right, so that's our little bit of introduction to the normal model today. We'll talk a little bit more about that again.